Welcome to this new episode of my lecture series on functional analysis. If you are joining me for the first time, I extend a warm welcome and strongly encourage you to become part of our growing community by hitting that subscribe button. Please don't watch from the sidelines, especially if you're a math enthusiast and are eager to sharpen your mathematical knowledge. And by the way, is it not curious how some people still resist hitting that subscribe button? It is almost like having access to a library but choosing to stay at the closest door instead. Quite funny, right? Well, remember that by subscribing, you are not just gaining access to knowledge, you are embarking on a mathematical odyssey that promises to enrich your understanding of mathematics and also provide you with valuable support in your education or career. So today our focus is on compact operators, an essential concept that serves as a cornerstone in understanding the behavior of linear operators. Just as a master key opens countless doors, understanding compact operators will unlock a multitude of analytical techniques and applications that will undoubtedly enrich your understanding of this fascinating topic. So in order to give you a broad picture of what a compact operator is, imagine you have a camera with a zoom feature, right? And you're trying to capture a detailed image of a distant landscape. So the zoom capability of the camera allows you to focus on specific areas, bringing distant objects closer, right? Now, let's think of the camera lens as the linear operator and the landscape as the space on which the operator is acting. A compact operator is like having a camera with limited zoom. No matter how much you zoom in, you cannot capture the entire landscape in detail, but you can still get a meaningful and relatively clear representation of a bounded portion of it. So in the context of functional analysis, this means that a compact operator may not preserve all the intricate details of the input space, let me put it like that, but it can still capture a meaningful and relatively well-behaved portion of it, similar to how the operator maps bounded set to relatively compact sets, for instance. Moreover, just as the camera lens limited zoom prevents you from capturing every detail of the landscape, a compact operator by its nature does not preserve all the properties of the original space, but still manage to capture some essential characteristics in a more simplified form. So let's get into the mathematics. So throughout this chapter, and unless otherwise specified, E and F. So E and F denote Banach spaces. Okay, so we start with the definition of a compact operator. So definition. A bounded linear operator. A bounded operator. G, right? Bounded linear operator from E into F, right? Is said to be compact. Let me put it in color. Is said to be compact if the image of the closed unit ball has compact closure in F. Right, the sum topology, of course. So maybe let me just specify it. in the strong topology. Okay, so this again, so this means, this is equivalent to saying that, this is just another way of writing. At the closure of this, the strong topology, that this is compact, right? You also say that the image of a closed unit ball is relatively compact. Right, where of course as I said, this is the closed unit ball. In A. Okay, so you can even kind of prove that this definition is equivalent to saying that, it's even equivalent. So let me put it probably this way. So the above definition is equivalent to saying that T transforms bounded set into relatively compact set. Right, and again this is equivalent to saying that any bounded sequence in, how will I put it, like it for any bounded sequence, say let's call it xn, right, in E, right, in the domain of the operator T, the sequence in the image sequence, right, the sequence call it Txn, T of xn, right, in F, right, has a convergent subsequence. Sorry, so all those definitions are equivalent, right? And also just to bring this to your attention, the definition, you can even forget about boundedness, right? You don't need it actually, because the compact operator is already bounded. So you can define, you can say that the linear operator, you can just use linearity, right? So a linear operator, the linear operator T is said to be compact if the image of the closed unit ball is has compact closure in F, right? So as I said, the compact operator is already bounded. So I put it here, boundedness. Oops. Let me write it properly. So boundedness is not needed, right? It's not a must, right? As compact operator is already bounded. Okay, sorry for that. Okay, I think we now know what the compact operator is. So the set of all compact operators from E into F, right, is denoted by we call it KEF, right? So, and when E and F coincide, when E and F coincide, we will write KE, right, instead of KEE, right, for simplicity. Okay, so we are ready to state our first theorem. So, theorem 611. So the set looks ugly. So the set of all compact operator KEF, right, is a closed linear subspace. Is a closed linear subspace of the space of linear bounded operator from E to F. Right, I mean, of course, in the topology, I mean, it's always very important to precise in which topology. So this is closed in the topology associated to the operator norm, right? And for the sum topology to this operator norm. Okay, so let's go into the proof very quickly. So the first step is, I think this is not straight. Good. So the first step is actually to show that the set of all compact operators is a linear subspace. So this is a linear subspace of the space of linear bounded operators from E to F. Right, so indeed, I mean, you're just going to show the most important property. So indeed, it is clear that the sum of two compact operators is a compact operator. Well, how do we see that? Well, you have multiple ways to approach the problem, but you can use the characterization of compact operators by sequences. So this means let's say let T1 and T2 be two compact operators, right? And say you have alpha and beta belonging to the field K, right? I mean, this is what we say it is R in our case, right? So let x and height be a bounded sequence be a bounded sequence in E, right? So since C1 is compact, we know that there exists, there is a subsequence. There is a subsequence. We will call it XNR, right? There's a subsequence XNR, right, of the original sequence such that, C1 of XNR, right, such that this sequence in the image sequence converges, right? Now, then, since XNR is bounded, right, because the original sequence is bounded, so the subsequence is also bounded. So since XNR is bounded, now we use the compactness of T, right, and T2 is compact, right? We can further extract another subsequence. So there is a subsequence. We call it this time XNRS, right, of the sequence XNR, right, such that T2 of XNRS, right, such that this sequence converges. So it follows that. Now you know that the sum of two convergent sequences converges, right? So it follows that the sequence, also by linearity, of course, follows that the sequence, we call it alpha T1 plus beta T2, right, of XNRS. So this sequence, right, converges. Thus we can conclude that alpha 1, wasn't alpha 1, alpha T1 plus C beta T2 is compact operator. It's compact, right? So this is probably not not the best approach, right? To not the best, but not the easiest or the fastest approach to deal with this problem. So another approach would be to see that alpha T1 plus beta T2, right? The image of the closed unit ball via this linear combination of the compact operators, right? So the closure of this is contained into alpha T1 of the closure of alpha T1 BE plus, let me write it down here, plus beta T2 BE closure, right? Now the goal, or the idea now is to observe that this is actually, compact, right? As image of, so this is compact as image of the product of two compact sets product of two compact sets via continuous map, right? Via the continuous map. Right, which at x, y, associate x plus y. So, I mean, we know that the product of two compact sets is compact, like this is a property due to Tikhonov, right? So, check it out if you are interested. So, the right hand side is compact, right? And so, and therefore, the left hand side is also compact, right? Because that's close subset of a compact set. So this would be another approach to show that a set of compact operators is actually a linear subspace of the set of linear bounded operators. Okay, so in the second step, now you have to show that KF is closed, right? That this is closed in this space. Okay, so for that, let Tn, right, be a sequence of compact operators, right? And say you have T a linear bounded operator, right, from E to F such that Tn converges in operator norms to T. So this actually goes to 0, of course, as n goes to infinity. So our goal is to show that T is actually a compact operator. So this is even a claim. So we claim that T is a compact operator, right? So this means that what we are saying is that the image of the closed unit ball, right, is compact, right? This is also another way of saying that it is relatively compact. But now, observe that, I mean, this, right, the image of the closed unit ball, right, is a subset of F, right? And F is complete. Right, and then if you remember, F is complete as a Banach space, right? So, and if you remember my lecture on the Azela-Scully theorem, right, where I recalled some properties of compactness and totally boundedness, then you should know that I mean the complete metric space, I mean pre-compactness is equivalent to totally boundedness, right? So for us to show that the image of the closed unit ball is pre-compact, it suffices to take that, I mean it's enough, right? Suffices to take that the image of the closed unit ball via T, right, is totally bounded. Right? So what does it mean? So this means that for every epsilon positive, right, there exists a finite epsilonet, finite epsilonet of T BE, right? So this means finite epsilonet means that for every epsilon positive, there is this, right? Phi I I in E, right? Finite sequence of element of F, right? I said finite sequence, so that means the cardinal of I should be strictly less. I mean, it's finite, right? Such that TBE, right, is contained into the union of the ball centered at Fi and radius epsilon I in capital I. Okay, so this is what you have to show. Okay, now since Tn converges in operator norm to T, right? So this means there is a rank starting at which the terms of the sequence Tn are close to T, right? So since this norm goes to 0, right, fix an integer n, put it in bracket, fix an integer n, right, such that the norm of Tn minus T, right, the operator norm of course, is actually strictly less than epsilon over 2. Now, since Tn, the sequence of compact operators, right, the image of the closed unit ball via Tn is pretty compact. So since Tnbe, is pretty compact, right, it is totally bounded. So this means that there exists Fi in capital I, finite sequence of element of F, right, such that Tnbe is contained to the union of the balls centered at Fi and radius epsilon over 2. So you have an epsilon over 2 net of Tnbe. So it follows that Tbe is actually contained into the union of the balls centered at Fi and radius epsilon I in I, right? This inclusion here actually follows by this actually follows by triangle inequality, right? By triangle inequality. Okay, so well, in fact, you know that there exists I0, right, in I, such that the norm of Tnx, right, minus Fi0, right, is actually strictly less than epsilon over 2. So this means that norm of Tx minus Fi0, right? The norm is F, of course, right? If I don't, precise, then you should be able to know, in which space I'm talking about the norm. So this is actually less, so by triangle inequality, if you insert Tn, right, this is less or equal than Tx minus Tnx, right, the norm of this in F, right, plus the norm of Tnx minus Fi0 in F, right? So, and then this, of course, is actually strictly less than epsilon over 2 plus epsilon over 2, right, because you can actually bound the first term by the operator norm and so on. So with this, we are done with the proof. of this first theorem. Okay, so now let's go to our second definition. I don't know what is happening with my throat today, but anyway. So definition: an operator T, right? I mean a linear bounded operator. An operator T belonging to the space of linear bounded operator is said to be of finite rank. Is said to be, let me write it in color, yes, to be of finite rank if the range of T, right? If the range of T, of the operator T, right? By the range, I mean RT, we denote RT for the range. This is similar to the image of T. This is nothing less than TE, right? If the range of T is finite dimensional. It's finite dimensional, right? So if you have a linear bounded operator for which the range is finite dimensional, then we say that that operator is of finite rank. So let's have some remark. So remark: so any finite rank operator is compact. Right? So let's prove this, right? I mean the proof is not long. Indeed, let T, right, be a linear bounded operator, right, be of finite rank. Right? So assume you have a finite rank operator. So this means that the space, I will call it Z, right? I mean the image of T. This means the space Z is finite. It's a finite dimensional. It's a finite dimensional norm space. Right? Furthermore, for any bounded sequence, say xn, for instance, in E, the sequence, I mean the image sequence, right? So the sequence T xn, right, is bounded in Z, right? I mean the image sequence is bounded in this space Z, I mean the image of T, right? I mean it is easy to see that it is bounded, right? Because take the norm of T xn, then this T is a bounded operator. I mean, so this is basically less equal than the norm of T times the norm of xn, but xn is bounded, so it's actually easy to see that Txn is bounded in Z, right? So by the famous Bolzano-Weierstrass theorem, I write it the German way, Bolzano-Weierstrass theorem. Probably highlight this. So by the Bolzano-Weierstrass theorem, the image sequence, right, has, must contain, it's a must contain a convergent subsequence, right? Hence T is compact, right? Because basically prove that for any bounded sequence Xn, the image sequence has a converging subsequence. So this is basically the proof, right? So of course, I mean, in finite dimensional norm space, every bounded subset is quite compact. Okay, so we can even derive some further properties from that. Sorry. So if either E or sorry, if either E or the codomain or F, right, is finite dimensional, right, then T is compact. I mean, T is a compact operator. So if one of the spaces, right, be this the domain or the codomain, right, is compact, then T is compact, right? I mean, actually very easy to see, right? Indeed. I mean, if the codomain is finite dimensional, then there is nothing to show, right? Because the range will be finite dimensional, so you obviously have a compact operator, I mean finite rank operator, and therefore a compact operator. So indeed, if E is finite dimensional, right, then we know that the rank, right, of T, right, the rank is just the dimension of the range of T, right, is actually let me just work it a bit to then the rank of T is less or equal than the dimension of E, right? So this means that the rank of T is finite once T is compact. I mean, T is a compact operator. So therefore we have the following property, right, that we can derive from compact I mean from finite rank operator. So this is corollary 6.2. Good. Okay, so let Tn height be a sequence. Say you have a sequence of finite rank operators, and let T, right, be a linear bounded operator from E to F, right, be such that the norm of T, I mean the operator norm of Tn minus T, right, goes to 0, of course, as n goes to infinity. Then T is a compact operator. Okay, so the proof is actually trivial, right? So I leave it to you, right? You can just put it here, theorem 6.1. Okay, so remark. So this is, I'll put a star to say that this is a very important remark, like crucial one. So the celebrated approximation problem. Oops. Celebrated approximation problem, right? I mean, this was firstly attributed to, to Banach, right, in 1932, right? And later on to Alexander Grothendieck, right? That was in 1955. Yes, I think so. So let me just okay. So the celebrated approximation problem attributed to primarily to Banach in 1932 and later on to Alexander Grothendieck in 1955 actually deals with the converse of corollary 6.2, right? So let me just highlight. So what does the converse of corollary 6.2 say? So the problem is given a compact operator. So given a compact operator, say T, does there always exist a sequence, let's call it Tn, right, of finite rank operators right, such that the norm of Tn minus T, such that sequence of finite rank operator converges in operator norm to T, right? Does this hold, right, for a T compact linear operator? Well, Grothendieck introduced and studied this problem in 1955. As I said earlier, it was part of his groundbreaking work on Banach spaces and operator theory. So, of course, the question was open for a long time until a Swedish mathematician named, I think, Per and Flo, yeah. Per and Flo discovered a counterexample in 1972. Of course, the original construction was quite complicated, and subsequently simpler examples were found. For example, let me put it probably here, with F being closing up subspace of LP, like for P. Well, I'll probably not mention it, right? But if you're interested into this, please mention it in the comment below, right? And I will be happy to provide you with some references in which you can find a detailed discussion of the famous approximation problem. So, but note that the answer, so let me just put it here. So note that the answer to the approximation problem, right, is positive, right? For answer to the approximation problem is positive. It's positive in some special cases. Right? For instance, if the codomain is actually a Hilbert space. Right? If put it in color, if F is a Hilbert space. So if F is a Hilbert space, then the converse of corollary, the converse of corollary 6.2 is actually true, right? If you give me a compact operator, right, from A into a Hilbert space, then I can always find a sequence of finite-rank operators that converges the operator norm to T. So maybe let's have it as a theorem, right? We put theorem star, right? Because it is the theorem that that we derive from the remark, the important remark. So let F be a Hilbert space. Oops, a Hilbert space. And say you have T, right? Your linear bounded operator. Your compact operator even. Defined from E into F. Then there exists, there is a sequence of finite-rank operators right? We call it, say, Tn, right? That which converges. Oops. Which converges to T, right? In the space of linear bounded operators, right? So this means that, as I said, we have put it in this color again. The norm of Tn minus T, right? This goes to 0. Okay, so let's go into the proof, right? Which is a bit lengthy but really instructive. Okay, proof. Assume F is a Hilbert space. So probably let me just highlight Hilbert space here. It's actually important. Okay, good. So let's go back to the proof. So assume F is a Hilbert space, right? I derive T compact operator from E into F. Okay, now put K to be the closure of the closed unit ball, of the image of the closed unit ball via T. Now, given epsilon positive, right, there is a finite, because K is compact, right? So there is a finite covering of K, right, with balls of radius epsilon, right? Say we have K. Sorry. So you have K is actually contained into the union of the balls centered at Fi and radius epsilon, right? I in capital I, right? And of course, those Fi's are element of capital F, right? And also capital I is finite dimension. Cardinality of I is finite. Now let capital G, right, be the vector space spanned by the Fi's. So say this is the span of the Fi I in I, right? This the vector space spanned by the Fi's. Now unset, put define T epsilon to be the projection onto the space G, right, composed with T, right? So put T epsilon so that T epsilon is of finite rank, right? So finite rank, right? Because since this is finite dimensional, and the vector space spanned by the Fi is finite dimensional. The handwriting is so big, very difficult. Oops. So since this is finite dimensional, okay. So our first claim is that, not our first claim, but the ultimate claim, right, is that the norm of T epsilon minus T, right? The operator norm of this strictly less than 2 epsilon. So if you show this, then we are done, right? Because you can basically take epsilon to be 1 over n, because epsilon is arbitrary, right? And then we have our sequence of finite rank operators that converges in operator norm to T. Okay, so let's prove this. Okay, for every x, right? Sorry, let us take in the closed unit ball, right? There exists an element I0 in I, right? Such that, let's call it 1, right? Such that the norm of Tx minus Fi 0, right, strictly less than epsilon, right? This is true because this is contained into K, right? Because TB is contained into its closure, but this closure is actually K. So, and K is contained to the union of the balls centered at Fi and radius epsilon. So this is true. So thus, oops, probably write it here. Thus, the norm of what? Of the projection onto G on composed, with T by 2x, right, minus projection onto this of Fi0 is actually strictly less than epsilon. And again, we are just kind of applying properties of what we know already, right? This holds because we know that the projection is projection is non-expansive, right? Non-expansive in the sense that the norm of this Kx minus this norm is less or equal than the norm of Gx minus Fi0, but this norm here is actually less than epsilon. Okay, so this means because Fi0 is an element of the capital G, right? We even have that the norm of this minus Fi0, right? So it's less than epsilon. I call this relation 2, right? As I said, this actually holds because this is an element of G, right? So which means that the projection, if you project any element of the space onto itself, you get the same thing, right? So if you combine 1 and 2, right? If you combine both 1 and 2, then by kind of triangle inequality once again, so combining combining 1 and 2, right? One obtains that the norm of this composed with T at x minus Tx strictly less than 2 epsilon, right? And this holds for every x, of course, in the closed unit ball. So this means that the norm, I'm just rewriting, right? norm of t epsilon minus t, at x, right, strictly less than 2 epsilon, and again for every x in the closed unit ball, right? So this means if you take the supremum, right, you get that the operator norm of this strictly less than 2 epsilon. So since epsilon was arbitrary, we conclude that t is the limit of finite rank operator. So t is the limit of finite rank operators. Okay, so this is the end of the proof. So people often say that Hilbert space has the approximation property, right? This is another way of saying that if you give me a compact operator, right, with codomain a Hilbert space, then it is actually the limit of finite rank operators. So more generally, so let me just write it. So more generally, sorry. So more generally, one sees that if t, if f, if f, the codomain right, has a Schroeder basis, if the codomain has a Schroeder basis, then the answer to the approximation problem is positive, right? So then the answer to the approximation problem is positive. Oops. Right, for every, no matter the domain, for every space E, right, and every compact operator T, right, from E into F. Well, why is that true? Indeed, let En, right, we assume that F has a Schroeder basis, so let En be the Schroeder basis of F, right? Now put Gn, right, to be the span of vectors E1 up to En, right? And also put Pn, that will be defined to be, this is the projection onto the space Gn, right? So this is the natural projection, right? So this is the natural projection operator. Then this sequence Tn equals Pn composed with T, right? So this is a sequence of finite rank operator, right? So this is a sequence of finite rank operators, and obviously converges in operator norm to T, right? So this will be, this is kind of the, the proof idea, right? Okay, so let's move quickly to proposition 6.3, right? What do we know about, if I take, so let me just take this, we let E, F, and G, right, be three Banach spaces, be 3 Banach spaces. Sorry. So be 3 Banach spaces, right? And let we call it. So let's say, right? Say you have a compact operator, right? No. Let's start probably with a linear bounded operator from from E to F, right? Sorry. So let's say be a linear bounded operator from E to F, and say you also have S, right, which is now a compact operator from F to G, right? Of course, you can respectively, I mean, T could be put it another color. I mean, T could be, instead of being a linear bounded operator, can be a compact operator from E to F, right? And S, a linear bounded operator from F to G, right? So if T and S are chosen to satisfy these properties, then S composed with T, right, is compact operator from E to G, right? So the proof is actually trivial, so it's actually easy, right? I will not go into that. So I leave it to you. Of course, if you have any problem, please feel free to drop it in the comment below, and I will be happy to assist you, or I mean to help you with details or whatever you want. Okay, so let's have what be the final theorem of this lecture. So theorem 6.4. So this is also known under the Schroeder theorem, right? Actually gives us I mean it gives us if I have a compact operator, is the adjoint also a compact operator? So this theorem actually answers these questions the positive way. So if T is a compact operator, right, from E to F, right, then the adjoint of T, right, is also a compact operator from the dual space on F to the dual space of E, right? And conversely, right, the converse is also true. And conversely. Okay, well, if you don't know what the adjoint is, just know that, I mean, saying that T star is the adjoint, I mean, the adjoint of T means that the duality pairing of FTS, right? FTS in this space, F star comma F, right? This is nothing else than the duality pairing of T star F comma X, right? In E star E. So if you have a T star that fulfills this property, then we say that T star is the adjoint of T. And this, of course, should hold for every F in the domain of T star. Okay, so let's go into the proof. So proof. So we'll start this time with the most difficult part, right? And go back to the easiest part. Okay, so we have to show. Let me just recall what we have to show. We have to show that the image of the closed unit ball, right, now in F star, right, where T star has compact closure. Has compact, I'll write it here, has compact closure in the dual space E star. Okay, for that we, of course, we use the characterization of compactness via sequences. So let's call it Vn, right, be a sequence, right, in the closed unit ball. F star, right? So those are linear bounded operator on F, right, for which the norm is actually, the operator norm is less or equal than 1. Okay, so we claim that T star Vn, right, which is the image sequence, right, has a convergent subsequence. Right, so in order to prove this, we are just going to show that we are going to show that we will first extract the subsequence, right, out of Vn, and then show that the image sequence of that subsequence, right, is actually a Cauchy sequence. Because we are in a Banach space, then that will allow us to conclude that it converges, right? So this is basically the main idea of the proof. Okay, so put K once again, right, to be the closure of TB, right, the image of the unit ball in E, which is a compact metric space, right, because T is a compact operator. Right, let me just write Y as T, the compact operator. Okay, now consider H, right, be a subset of the space of continuous function over the compact metric space K, right, defined by H is actually the space of function phi n, right, which maps x, an element x of K to the duality pairing of Vn comma x, right, and this of course for every n greater equal than 1. So of course, let me put it in color. This is the duality pairing, right? So Vn comma x in the space F star comma F. Okay, so maybe instead of using x, I should have used probably y. So, but anyway, so H is defined this way. So of course, it is easy to see that H is bounded, right? The norm of n is finite, right? And also that H is uniformly equicontinuous. Looks ugly. Oops. So you have equicontinuity of H, right? But this actually follows from if you want to check it, so this follows from the continuity of the Vn side. Okay, so basically the assumptions of the Ascoli-Azera theorems are satisfied. So the assumption. So I strongly invite you to watch my video on the Azera-Ascoli theorem, right? So the assumption of the Ascoli-Azera theorem, right? I think this was actually theorem 4.25. I'll put the link at the upper right corner for your reference. Just highlight those. So the assumption of the Azera-Ascoli theorem are fulfilled. So this means that H is pre-compact, right? So which is another way of saying that there is a subsequence denoted, let's call it phi n k, right? That converges uniformly on k, right, to some continuous function phi in this, say k, right? Space of continuous function over the metric space k. So this means, that phi nk minus phi, the n infinity norm of this actually goes to 0, of course, as k goes to plus infinity. So in particular, right? In particular, as this is a subset of k, right? You have that the supremum, right, of the absolute value of vnk comma tu minus phi of tu, right? Oops, this actually goes to 0 as k goes to plus infinity. This is of course over the u in be, right? So there's the supremum of the absolute value of vnk comma tu, right, minus vnl comma tu, right? This actually goes to 0 as k and l goes to plus infinity, right? You can just, to see this, just need to kind of use triangle inequality and then, nothing complicated. But now observe that this quantity inside here, right, is again, using the definition of the adjoint. So this is again T star vnk, right, minus T star vnl, the dual pairing, the duality pairing, right, of this, right, T star comma e. So this means that the norm, the operator norm of T star vnk minus T star vnl, right? The operator norm of this in A star actually goes to 0 as k and l goes to plus infinity. So this means that T star vnk is a Cauchy sequence. So this is a Cauchy sequence, right, in the dual space E star, right? But this is actually Banach space, right? Since this vnk, right, converges in E star, right? Let me just highlight this, that this is a Banach space, right? So that subsequence converges in E star, so, and then you're basically done. Good. So the first implication holds. So now let's have a look at the reverse. Now conversely, assume that the joule, not the joule, the adjoint, sorry, the adjoint of T, right, is a compact operator from the joule of F into the joule of E. Right, we already know from the first part So you already know from the first implication that the adjoint of t, right, t star star, is a compact operator from the bijoule of A into the bijoule of F, right? In particular, t star star of the closed interval in E, right, has compact closure in F star star, right? I mean, this is due to the fact that, I mean, the closed unit ball in E is actually contained into the closed unit ball in the bijoule, right? Remember, we have the canonical embedding of E into the bijoule. Okay, but TBE, right, is exactly equal to T star star of BE, right? Sorry, very equal to the T star star of B, right? This is due to the fact that in fact T star star, right, restricted to E equals T, right? And we also have that well, you can actually say it very easily also. I mean, if you have phi tx, I mean, this duality pairing in F star comma F, right? This is again duality pairing of T star phi comma x, right, in E star E, right? But this is again phi comma T star of x, right, in, well, in F star comma F, right? And this is of course for, I mean, for every x in the, I mean, B. So TBE is exactly equal to T star star of B, and F is also closed in the bijoule, right? Because, well, this is, oops, right? This is because I mean, F is a Banach space, right? Due to the fact that F is a Banach space, and also that I mean, the canonical embedding iota of F, right, from F into the bijoule is an isometry. So due to that, I mean, you can conclude that hence the image of a closed unit ball, right, has compact closure in F. Well, you still don't get, so this is the end of the proof, right? Well, if you are still confused about why this has compact closure, well, observe that, I mean, the closure of this in F, right, the closed unit ball where T, the closure of that set in F, this is exactly equal to iota of F, right, of the closed unit ball in E, right, but this now in F star star. So this is iota of F of the, I mean, of TBE, right, the closure of TBE, but in F star star. But we saw that use another color, so that this is exactly equal to, oops, to T star star of BE, right, the closure of this in in F star star, right? And this is actually compact. Now, because iota is an isometry, probably now because iota of F is an isometry, right? This the closure of TB in F is compact as well. Okay, so I hope this is clear enough. So let's have a final remark. I think I mean the video is getting long, so let's end this lecture with this remark. Okay, let E and F, right, be two Banach spaces, and let T be a compact operator, right, from E into F, right, if say UN, right, converges, let me write fully, converges weakly to U in E, right? So this means we have something like this: UN converges weakly to U in E, right? Then TUN, I mean the image sequence TUN, right, converges strongly to TU, right? So well, I invite you to prove it, right? It's a really nice proof and not difficult. So, and of course, if you have any problem, please put it in the comment below, and I will really I will be very happy to help you, to assist you. So the converse is also true, right, if the space is reflexive. The converse is also true if E is reflexive. Okay, so this is actually a striking property, right, that if you have a weakly convergent sequence in E, right, and then you have a compact operator, then the image sequence actually converges strongly to TU. And this is very I would say even extremely helpful in optimization, right? We actually like to use this weak to strong operator, I mean these compact operators, right? They are really helpful. So I mean, of course, I will probably come back to that when I will discuss optimization with PJs, right? So well, so this is the end of this lecture. So thank you for joining me, and see you in the next video, where we will probably talk about the Rees-Freedom theory, right? So stay tuned for more exciting adventures.